Hi, we're going to take a look at the Multivariate Calculus Study Guide. What is it? I think the best description is that it's a manual for how to use Maple in a multivariate calculus course. There's a pedagogical slant to it, but it's also a demonstration of all of Maple's syntax-free tools, so that a student in a multivariate calculus course that has Maple available has a guide to how to do all of the computations and all of the investigations in that course in a syntax-free manner. They don't have to learn any commands. But I will show you that for the instructor or the student who wants to see how to use Maple via its command set, that's also included. So what's the layout here? This is the table of contents that launches when you begin looking at the product. It has a preface, as you would expect a book to have, and it gives you some information about what this guide is about and how it builds on what you might have seen in the Calculus Study Guide. So we navigate back to the table of contents, and you'll notice that the preface still exists here as a separate tab. You can leave it there, or we can put it away. So I'd like to show you the rough outline and then give you some examples of what you would find inside the study guide. You'll see that it has 9 chapters and is organized pretty much in the order that the typical multivariate calculus course is organized. At the beginning of the course, typically there is a unit on vectors, lines, and planes as a way of introducing the student to thinking in 3 dimensions. Everything is linear. Then you start to bend those lines and planes, and you get curves, and eventually you'll get surfaces. Then functions of several variables. What are they? What do they look like? How do you draw their graphs? How do you interpret their graphs? Then differentiation. So we have partial differentiation. So within each of these chapters, you would see a number of sections. And so here you have a collection of the sections that you would run across in vectors, lines, and planes. And each chapter has a chapter overview, so I'll just show you this first chapter overview. You can again access the sections, and there's typically an introduction, gives you some rough idea of what's in that chapter. In this introduction, there's one paragraph that I think is important, and that's this one. It states that vectors throughout this text are written as bold Roman font objects. We do not use the arrow over the top notation or anything like that. Maple can write it. You can see here Maple can write that. But this object cannot be assigned to without making it an atomic variable or an atomic identifier. Okay? This a pair of symbols, the letter and the arrow, have to be locked together as a single object. And that's just extra work, and I opted not to do that. Making something bold and Roman is actually simpler than converting all of these symbols to atomic identifiers. So those are the kinds of bits of information that one would run across in an introduction. Okay, so that's a quick look at the section or the chapter on lines and planes. Space curves, again the same idea. You have from position vector representation of a space curve down through the Frenace array, formalism for analyzing a space curve, functions of several variables, graphs. Here's where I have limits and continuity in the quadric surfaces, and then partial differentiation. What are partial derivatives? How do you take them? And where does this lead you? Directional derivative, which leads you to a gradient vector, tangent plane, a surface normal. And here's where the differential is introduced. Optimization, both unconstrained and constrained, and then optimization on a closed domain. And I've separated these three topics to make it easier for the student to make that distinction between what kind of a problem are they facing. And finally, differentiability down at the end. Very different from single variable calculus, where you first define a derivative, and from a derivative you define a differential. But in functions of several variables, a function that has a differential is differentiable. So it's just the opposite. So those are the kinds of things that are summarized, because this is taken not as a full calculus text. We assume that the student has a calculus text, and we don't want to create another one. We just want to summarize what they need to know and then illustrate how to apply Maple to all of that calculus. A double integral. Okay, so this is the double integral, different from the iterated integral. The iterated integral is how you evaluate the double integral, and for nice smooth functions, you can evaluate the double integral by iterating. Typically, when in calculus, multivariate calculus course, when you say double integral, you're typically thinking in terms of the iterated integral. And then applications, area, volume, surface area, moments. Same thing with triple integral, same breakdown of triple integral. And then chapter 9 is a chapter on vector calculus, where we use primarily the vector calculus package. And then at the bottom there's an appendix where we try to summarize things about Maple that are useful for the student who has not had previous exposure to Maple. For example, here where we talk about the working environment is document, there's a worksheet. There's typeset math, there's linear or one-dimensional or textual input. How do these elements work together? Then how do you do arithmetic calculations? How do you reference objects after you've got them on the screen? Then how about algebraic expressions? This is arithmetic, this is algebra, and you have operations on algebraic expressions. How do you evaluate something? You put a string of computations together with operators and stuff. How do you evaluate that? How do you implement coordinate geometry? Because there's a lot of coordinate geometry in multivariate calculus and some trigonometry. How do you implement a function, not just an expression, a function? And how do you draw graphs in Maple? And how do you solve equations? How do you factor and collector terms in algebraic expressions? And then there's a section on additional resources, and you see here there are links to a number of items that are available on the Maple website. Here the student portal is a portion of the help system that's built into Maple that answers roughly 150 questions on the order of how do I do this, how do I do that. They're organized in some logical arrangement. That's a very useful tool. There are a number of Calculus 1 recorded demos. There are recorded examples in both Calculus 1 and Multivariate Calculus. There's a student help center. There are training videos. There's a student center. There's a series of clickable calculus, syntax-free computations in not only the calculus, but differential equations, linear algebra, and vector calculus. The Maple user manual is built in. It's the actual user manual that Maple supplies, and there's a teacher resource center. So there are all of these additional opportunities to get a glimpse of how to do stuff in Maple. Okay, so let's take a look at each of these chapters and try to get a glimpse of something from within each chapter. So in chapter 1, I'm going to take a look at something having to do with lines. So this is the section on lines. You'll see the structure here. There's a summary of what a student needs to recall from their study out of their calculus book. So here I've summarized various representation of a line in R3. And then there's a set of examples. So here's an example I'm going to do. Distance from a point to a line. So this is what a typical example looks like. Here's a statement of the problem, and then there's a solution. And you'll notice that the solution comes in generally in 3 forms. There's a mathematical solution in which Maple does not appear. It's the way this solution would look in a textbook. So in this problem, we have a point, we have a line. This A is a fixed point on the line, but it's given as the position vector to A, and here's the direction vector for the line. So here's the fixed point A on the line. Here is the direction vector. This is the point P. By subtraction between A and P, you get the vector U, and you project U onto the line and orthogonal to the line. So this blue vector, orthogonal to the line, has as its length the distance from the point to the line. That's typically how this is done in a multivariate calculus course. And here's the computations, right? This is the orthogonal component of U. And this is how it's computed, this projection, and so the computations follow out here. Okay. There is an alternative, and so it's referenced back here to a previous table where distance from a point to the line is represented in this fashion. And so that formula is implemented here, and you see that you get essentially the same answer by both techniques. Okay, so then the syntax-free solution is given next. So here I have installed the Student Multivariate Calculus package, and then these are the stage directions for what you do, and here is what it looks like when you do it. This is the point. Now in Maple, points are typically given as lists, and the square bracket gives you a list. So this is the point. This is the vector V. These angle brackets are written with inequality symbols. So we make this sequence point and vector, and then right click. Now I'm using a Windows computer, so I have a 2-button mouse, but you have the equivalent on systems that have only a 1-button mouse. There's an equivalent. Okay, right click, and you see in this pop-up menu, which is tailored to what I clicked on, the Student Multivariate Calculus package, because I just installed it. Lines and planes, line. So you select line, and you get a pop-up where you can set the coordinates. The defaults are XYZ. I leave it as XYZ, and you have line. That is essentially just the name of a module or indicator pointing to a module where all the information about this line is stored, and you can query it for a variety of its properties. And then I'm going to assign it a name, so assign to a name, and here's where you would give it a name R. All right. So then here we have put the point and the line. See, R stands for the line. And you right click, Student Multivariate Calculus, lines and planes. We want the distance. So you select distance, and Maple gives you this value. And then the pop-up menu, you have an option to combine these two radicals, and here you can approximate to some fixed number of places. Okay, so you have an answer, and that's the pedagogical bent that I pointed out. First thing is, how do you get Maple to give you the answer? What is it that you're trying to do? What does an answer to this question look like? What is the most efficient way that you can get it? And then you can use Maple to implement the computation as you have seen in a textbook. A typical textbook will use vector methods. So here we are defining the various quantities we need, A, P, and V, into difference U. And here is the vector approach to obtaining that distance. There is a tool called a task template, and the path to that task template, Tools, Task, Browse. So I'll do that once for you. Tools, Tasks, Browse. And so what comes up is a table of contents. There's about 350 task templates, and you'll see here that the path says go to linear algebra, visualizations, projection plot onto one-dimensional subspace, and there is the task template, and you can insert it into your workspace by clicking one of these insert buttons. Default content means you get all this extra verbiage. Minimal content means you get enough to make it work. And I've already got it embedded here, and I've populated it. I want to project U onto V. This is the projection, this is the orthogonal component, and this is the picture that you try to draw, but it's drawn for you, and you can see this is the line, this gray thing here, there's your line, so that's the vector V. This is the vector U. Here is its orthogonal component, and it's the length of that red vector that gives you the distance. So you see you're using Maple to get some insight into what it is you're trying to do. Here I've extracted this vector, pulled it down, gotten its norm. So you right click. There's a norm operator here, or you can go down here and there's a norm operator here. Okay, and then there is a coded solution. So this is what it would be like to solve this problem using Maple commands. So again, you would work within the Student Multivariate Calculus package. It's already been loaded. You wouldn't have to reload it. Define the line with the line command. Obtain the distance with the distance command. And float with the eval_f command. And if you want to work vectorially, you can define the vectors. And here you see a feature of assignments. This is a sequence of names, and this is a sequence of values, and the assignment maps as you would expect. First goes to the first, and second goes to the second, so it's a little bit of efficiency there. And then to compute this quantity, you would need dot product divided by dot product, and then the norm of the resulting vector, which would be this vector, and you get this answer. A quick look at something from Chapter 2, Space Curves. You can see you have things like arc length and tangent vectors, and work your way down here to the Fourier formalism. I'm going to go here in this section 2 on arc length and examine this notion of arc length as a parameter. Typically, it's very difficult to do. You normally do not ever have arc length as a parameter. So in Essentials, you see there's a table that summarizes arc length function. And here is the statement that we want to illustrate. If you have a curve parameterized by arc length, you take the derivative with respect to that parameter, the length is automatically 1. Okay, so that's what we want to illustrate. And there is this example where we'll tackle that. So you'll notice you have to choose your curve very carefully in order for you to be able to carry out the exact calculations that let you see or experience this result. So here's the curve. You need the arc length function for that curve. You have to invert and reparameterize, and then you can take the derivative and the norm. Okay, so mathematical solution. We draw a picture of the curve, makes it more concrete. And so this is the length of the tangent vector. So this is the norm of the RDP. So now you can write the arc length function, which is an integral. And in order for it to come out to be a function of p, you have to change the integration variable to a dummy variable. You get this quantity, and then that's what you have to invert p as a function of s. So that's quadratic. So p is a function of s. There are two solutions. You pick the one that's going to remain positive, and then you take that expression and you put it into p in r. So it becomes p of s, and so that's how you get r of s. So there's r of s. You do a little cleaning up. Now it's ready to take a derivative. You take the derivative, you take the norm, do some algebra, and you get 1. Okay, so that's what is being pursued. And here's how to do that Maple without using commands. So load the student multivariate calculus package, define the curve as a position vector, take the derivative and its norm, integrate that. So I left that as p, so I integrate to t. And then down here, when I write s of t, I realize that what I really want to have is s of p, so it's just a question of transcription. Here's the solve step. Okay, so make use of Maple's pop-up menu. You solve, you get two solutions, and you drag over the one that stays positive. So here is r as a function of p, and by using evaluate at a point, you replace p with p of s. So you get this, and then you do a simplification and you give it a name. And so then in part C, you take the derivative, because this now has arc length s, take derivative with respect to s, take its norm, get 1. And to do that with commands, we would make use of the assignment operator here. Here is the derivative, its norm, integrated. Here is the result of that integration, and again you write s of p as p squared plus p over 2. Here is the solve step. Evaluate command, the eval command, makes the substitution. There are two solutions here. P sub 1 is this first solution, and it's wrapped in a simplify. And then part C, here is the derivative, here is the norm, and you get 1. In chapter 3, the notion of a function of several variables is introduced. And so here in section 1, functions in their graphs, limits and continuity, and then the quadric surfaces, because the surfaces are most often used as examples in multivariate calculus. So I'm going to take a look at something here in section 3. Again, essentials. Well, here is a table of the quadric surfaces, some comments about each of them, and then some examples. I can pick the very first example here if you like. So we have this equation, it's a quadratic in x, y, and z, and we have to put it into standard form, identify it, draw its graph, and then discuss the nature of level curves and plane sections. Okay, so what does Maple offer by way of help in this task? So there is a graph drawn down there, okay? It's put into standard form, and then level curves, circles, plane sections, hyperbolas. Okay, so here you see the surface, but here you see the surface with a slider under it. This slider is providing images of the cutting plane, x equals. Okay, so x equals this value, you see the cutting plane making hyperbolas. Right? So you've identified the surface as a cone, and you can see level curves and plane sections. So that's what a typical textbook would try to provide, but it cannot provide that interactive application where you can actually see the plane sections moving. Okay, so now how would you do the computation in a syntax-free manner? Well, we're going to load the student pre-calculus package, because that package gives you the best access to the complete the square option. There's a complete the square option in top level. Without loading that package, there is a complete the square option, but you would have to complete the square in x, y, and z separately. First x, then y, then z. In the student package, you can complete the square with respect to all three variables simultaneously. However, the implementation there only applies to an expression, not a function. So what we did was we right-clicked and we took left-hand side so that we can get rid of the equals 0. Then you can complete the square. Well, I would have to actually load the student package for you to see that. Okay, so you get to here, and in the student pre-calculus package you can complete the square with respect to all its variables. Okay, so we have completed the square. We want to make this back to an equation, so we have put back the equals 0. Let's see, it would be done here on the conversions, right? Equate to 0. Okay, so then you want to move this term to the right, and the way I did that was to select it, and you get this pop-up which says, okay, you want to subtract that from both sides. Very good. This is what it will look like when you're done, and you select that. That's what happens. Then you want to divide by 4, so you select that 4, and there's again a pop-up. Oh, you want to divide by 4 everywhere? This is what it's going to look like. You select that, and that's what you get. And so we've gotten to standard form simply by syntax-free manipulations. Okay, now to draw a graph, this is a discussion of how to use the plot builder to draw a graph. So if you went back here to the original equation, you would have plots and a tool called the plot builder, which is an interactive tool for drawing graphs. This is a discussion of how to organize the panels in the plot builder to get the graph that we showed in figure A. And then here, these manipulations are done by means of syntax. Okay, so if you invoke the complete the square command in the student calculus package, you can work on all variables. And here, when you're working with the command, Maple doesn't have this restriction about an expression, not an equation, the way the pop-up menu does. Here I have added z minus 2 squared to both sides, and here I have moved or divided by 4 on both sides. And f equals 0 defines the cone implicitly, so implicit plot 3D, and these are all the various options to get that graph. In chapter 4, where we talk about partial derivatives, we have sections where the partial derivative is explained. How do you compute them? Higher order, chain rule. Then you start to apply derivatives to various tasks. And here, one of the tasks is obtain a surface normal, a normal on the surface, and then draw a tangent plane at that point. So let's take a look at something from that section. Okay. So you have a list here of essentials. And the essentials are, if the surface is defined explicitly, the easiest way to get a normal to that surface is by the recipe minus fx minus fy, 1, where the subscripts represent partial derivatives. And if the surface is given implicitly, then the gradient vector will give you a normal, because the gradient is orthogonal to the level sets. Right? So this recipe is easily obtained by writing z minus f. That makes the description of the surface implicit. Take the gradient, and this is what you have. But that distinction, in my mind, is always crucial because students mix this stuff up, and I've always thought that it's really helpful for them to understand the difference between the two cases. Okay, so that's the kind of thing that you would find in essentials, these key notions that have been picked out to say, you know, this is really what you want to understand here. Okay, so let's just pick an example. The first one be fine. I have a surface, a place, and we want to get a tangent plane and draw a picture. So again, mathematical solution. Here's a picture of what you're trying to accomplish. This is what the surface is going to look like. Here's a tangent plane at the point that's been prescribed, and there's the normal vector. So you have a point on the plane, and a normal for the plane, so you have all the ingredients that you need to obtain the equation of the plane. So the normal is going to be obtained as minus fx minus fy1. This is what the normal is. This is the vector equation for a plane. R is the generic position vector, xyz. This is the point on the surface. I call it Q. Here are its coordinates. You're working at x and y are 2 and negative 3, and then this is the value of f at that point. And here is the calculation, and here is the resulting tangent plane. Okay, so let's work in the multivariate calculus package. Here I've loaded it. Here I have defined f of x and y as a function. Right, you write the equation and then you use assign function. And then all the machinery of building a function takes place. And here is the point q, which is 2 minus 3 and f of 2 minus 3. So we'll let Maple do that work for us. Okay? So we want minus fx minus f of y1, or these are partial derivatives, and those are obtained by looking here in the calculus palette, and there is a partial derivative operator in that calculus palette. Let's see if I can get that to close. All right, and that's what I used. So you write that, and what I suggest is that you use evaluate and display in line. It does exactly that. It evaluates the derivatives, etc., and displays in line. So it puts the equal sign in and puts it to the right of the equal sign. And the hotkey for that is control equal. And so this is the vector. And you want to evaluate that at the point where x has the value 2. And so this is the normal, and then we give it the name n. And so this is the point. This is the normal. Make plane. That's done through the context menu. I haven't loaded the student package, so Maple doesn't know what these things are. You get a plane object the way we had earlier a line object. Here's a module that contains all the information about the plane. Right click and get its representation. There's the equation of the plane. Okay, so we have gotten Maple to give us the equation of the plane with a minimum of fuss. Okay, now you want a solution from first principles, then you need position vector to the point q. So here is q as a list point. You convert it to a vector, you give it the name a, and here you define the generic position vector, and this is the vector form the equation of a plane. You implement it and you get the same equation of the plane. The commands are working still within the student package. This is what it takes to define a function if you don't use the context menu. This is the name of the function. You have the assignment operator. This is these are the variables, the arguments to the function, and you've got to type in that arrow. You can use a dash and an inequality symbol. It will form an arrow, or you can get it from one of the palettes. Or there is a template for defining functions. All right, see here, you can use this template, and it'll put the arrow in for you. All right. But I got tired of explaining an arrow to my students, and would have been very happy to have context menu computations available while I was teaching, but I retired from teaching before Maple made these tools available. Okay, normal vector. Here is minus the derivative with respect to x minus the derivative with respect to y and 1, and you evaluate that at x equals 2, y equals -3, and you give it the name n. So you form the plane with the plane command, and you wrap it in the get representation command, which gives you the equation of the plane, and there you go. There is in the vector calculus package a tangent plane command. So if you give it the rule, here this would be the rule for the function, at the location x equals 2, y equals -3, you would get the tangent plane given parametrically. This is a vector, x is x, y is y, and z is this function of x and y. Okay, so for those who want to have their students learn commands, I would point out that this is much more difficult to read and interpret than that. That's my opinion. and there are different opinions out there. So you pays your money and you takes your pick. In Chapter 5, we start talking about integration. We begin double integral, what it means, limit of the Riemann sum. For continuous functions that you see in multivariate calculus, you can evaluate a double integral by iteration. So then the details, curve boundaries, changing order, dx, dy, dy, dx, numeric evaluation of iterated integrals. You don't normally see that in a multivariate calculus course. That's something that comes up in a numerical analysis course. But since Maple can do it, I threw it in here. So for those integrals which don't evaluate in closed form, you have a way of getting a value. Changing variables. Let's take a look at that. So what are the essentials? The essentials are essentially the Jacobian. So we assume that the student has seen that. We remind the student when you change variables in a multiple integral, you're going to need to remember about the Jacobian. Now here's an example that we'll use to help set ideas. We have a simple function. We're going to integrate, get the volume under it. But we're going to integrate over a region in the xy plane that's a triangle defined by its 3 vertices. Then we're going to make this change of variables, and we're going to integrate again, and we see that we get the same thing, and we want to see what happens under this change of variables. Okay, so there's a mathematical solution, and it begins by delineating the 2 regions, one in the xy plane and one in the UV plane. The xy plane is your triangle. To integrate, you're going to have to integrate from this green line to the black line, then write another integral to integrate from the red line to the black line. Whereas the image over here in the UV plane is a right triangle oriented so that you can get away with one integral, one double integral. If you go dv du, you can go up this way, take one integral. So that's the essence of what this example is presenting. Okay, so data. Equations of the lines of this triangle in region R, and then the mappings back and forth. Okay, the mapping from R prime to R, that's what this says. If you know a UV pair, you plug it in this these equations, and you get an XY pair. So you're back over here. And to map from R to R prime, you know an XY pair, plug them into these equations, and you get a UV pair. And so those are the mapping equations. You need a Jacobian matrix. So this is going to be the Jacobian matrix that you need. It will have the value -5. And what is this Jacobian matrix? It's the Jacobian matrix of the mapping from R prime to R, because you are differentiating x and y with respect to u and v. Okay, and you see the 3 and the 2 and the 7 and the 3, that's where these numbers came from. Okay, so that's the Jacobian matrix you're going to need. You make the change of variables in the scalar function f, x of u and v, y of u and v. So this is all the arithmetic that gets you to this new integrand. Okay, that new integrand shows up down here, multiplied by the absolute value of the Jacobian, one integral. And this is the integration in the xy plane, region R. It takes 2 double integrals, and both give the same value. Okay, so that's the mathematical solution. Lays out what is he trying to accomplish. And here is a Maple implementation without commands. So you need some data here. Okay, so this is a list of the 3 points that form the triangle in region R. And give the list the name P. So the first element of P is this point, second element is this point, third element is this point. This is the function that you want to integrate. And then you need expressions for the mapping. So here you have u and v as functions of x and y. But in order to keep the symbol lowercase u and lowercase v free as variables, we assign not to little u and not to little v, but we assign to big U and big V. Right? So now we need the equation of those edges. So P1, P2, that's a pair of points, first point, second point. Make a line, get its representation, isolate this for y. All right, so we've gone down here to solve, and we use isolate expression for y, so that we have the edges in the form y equal. And then we need a name. So I picked S. 1, 2 means first point, second point. 2, 3 means second point, third point. And 3, 1 is third point, first point. And then you can write the integral. So I make use of the calculus palette. There is a multiple integral, double integral template for definite integration. Okay, put that into place and fill in the boundaries. So you're going to integrate 1 to 3, then 3 to 4. That's where it splits. Lower line, upper line. The upper line stays the same for both integrals, but the lower line changes. Evaluate 160 over 3. Now let's go to the RPrime region. Okay, so we need to solve these equations, this mapping equation for u given as a function of x and y, v given as a function of x and y. We would need to solve for x and y as functions of u and v. And that's why I don't want to assign to little u here, because then I couldn't write a little u here. Okay, you would not be able to write these equations if you did not change this name. So write the equations, pop-up menu, you pick solve, you get x as a function of u and v, y as a function of u and v, and it's a set, call it capital S. Okay. Now we want to get the Jacobian. All right. So the Jacobian requires that you get this bit here and this bit here. So here's a way to do that. I use the evaluation template. Now that's in the expression palette, evaluation template. That's, where is that guy? That's this guy, evaluation template. Okay, that's what I'm making use of. I'm evaluating something at this value. Okay, so that's what I'm making use of. And what I'm evaluating is the name x. So keep in mind what this set looks like. Okay, this set S. I'm evaluating the name x at the information in this set, but x has this value. Okay, x has this value. You can see when I make that evaluation, x evaluated at the set S has this value, and I want to give that a name. I don't want to give it the name little x, I give it the name big X, and I do the same thing for y. So now I can make the list xy, which is now the two expressions that I need, and then there, well, I didn't load the package. Pop-up menu has the Jacobian command in it. If I load the package first up here someplace, then you'll see where the Jacobian command resides. Where did that go? Here. Student Multivariate Calculus. Under Differentiate, with that list, the only thing that makes sense is the computed Jacobian, and there's your Jacobian. Okay, now if you want to do it from first principles, then this is the matrix you need. And I've used the matrix palette to insert the matrix, and the calculus palette to insert these partial derivatives, and it's computed, and there is the matrix, Jacobian matrix, and under standard operations you'd find determinant, and you got the -5. Okay, so now we've got to convert each line in the R region over to R prime. So the line had the equation y equals, right, and under the changes x equals y equals in S, this is what you get, because this is really the y, this is the other stuff. If I move everything to the left, it collapses to a multiple of v equals 0. So you get one equation is v equals 0. Here, this edge becomes v equals 1 minus u, and that becomes the hypotenuse of that right triangle. And this edge, again, is a multiple of u, so u equals 0, v equals 0, and the hypotenuse. You make the same substitution into f, so this becomes the new integrand, and you're integrating 5, absolute value of the Jacobian, times the transformed integrand, new boundaries, and you get the same value, 160 over 3. And here is what it looks like if you do that via the command set. So first you have to put in data, right? So here the colon equal operator, you're making functions, okay, use arrow notation. So for the lines, use the line command, and when you use get representation, you tell it, give it back to me, the representation, in the form of an equation. And then you have to isolate y, so you get these 3 equations for the edges. Now, the int command with a capital I is the unevaluated integral function, or integrand, and then the ranges, and that's in a list. And you need 2 of them, and the value command evaluates that. Okay, so that should have evaluated. The value didn't show up here, but it's 160 over 3. And then this is the calculations over in region R prime. So you need to invert the transformation equations. So there's your solve for the inversion. Here is where you're computing the Jacobian. And the Jacobian command can produce either the Jacobian matrix, or if you say output equals determinant, you get the actual Jacobian, which is the determinant of the Jacobian matrix. And here we're doing the same thing about transforming each of the lines. So this eval is the equivalent of the evaluation template, and then moving everything to the left, you get v equals 0, v equals 1 minus u, and u equals 0. You make the replacement in the integrand, again, eval command to make that substitution, and then the int command for integration. And again, here the value, for some reason or other, disappeared from this list, but it's 160 over 3. Well, I think there's time for one more example, and I'm going to take that from Chapter 6, Applications of Double Integration, and I'm going to look at a volume question. I'm going to find volume, and here we have a discussion of the essentials, double integral. If you want volume, you have to know where the function is positive. If you want double integral, then you just integrate, and what happens, happens. Simple example, just to show you some of the tools that are available for working with double integrals when you want to find volume. Okay, so here I have a function, xy, and I have a region bounded by this parabola, the x-axis. Here's a mathematical solution, and you immediately have an image of the region of integration. This is the volume you want to compute. The function, the integrand xy, here in this region is this surface, and the parabola, you can see the bounds around, bound for the parabola. Okay, and so integrate dy dx, you get 1 over 20. Integrate dx dy, you get 1 over 120. And here you have to invert this parabola to get x as a function of y. It's quadratic. You get 2 branches, and those you split this down the middle, and you get the 2 branches. Okay, so that's what you would see in a textbook. That's how I would be able to present it in a textbook. To do this live, we have a definition of the integrand down here, and here is the bounding parabola. Okay. And here I solve x as a function of y. You get these 2 solutions, and together that sequence I call capital X because I can reference the branches as either the first member of x or the second member of x. Okay, so here is the integrand. I right-click on xy, and since this package, Student Multivariate Calculus package, has been installed, you have access to integration in several variables, and this says, okay, you want to iterate this integral, and you have a pop-up, and the variables are x and y, Cartesian coordinates, okay, and then the bounds, and the order in which you want to integrate it, dy dx, dx dy. So if you change this to y, then that becomes x, okay, and the outputs are, you can get the value, just a number, you can see the inert integral, or you can see the integral evaluated stepwise. Okay, so that's what's been selected here is just the value. The integral, the inert integral. So this is the integral, and then that's evaluated by right-clicking and evaluate from inert. And this integration here and here, that's done by the use of the calculus palette templates. Okay, so there's a more direct way of entering the integrals. So that is the integrand dy dx, dx dy. And so dx dy makes use of these 2 branches. Okay, this is the lower branch, this is the upper branch. So the x2 is the lower branch, x1 is the upper branch, and in both instances you get 1 over 120. And then there is this other tool. Okay, you see it's a test template. It tells you where to find it. It's in Calculus Multivariate on the integration. Visualize in regions of integration. So for Cartesian coordinates, 2 dimensions, you make your choice, dy dx, dx dy. So dy dx, and it tells you, okay, this is what your integral will look like. You have an integrand here. So you give the integrand, and then lower bound, upper bound. So the lower bound is 0, the upper bound is the parabola, and x goes from 0 to 1. That's the value of the integral. And then you get these graphs. This is a graph of the region in the xy plane over which you're integrating. The arrow indicates that you're going to integrate dy first. Okay. And here is the volume that you will end up computing. Right? The quotes around volume means not every one of these integrals that you set up this way is a volume, so most of the time it's going to be a volume, but it doesn't have to be a volume. And then here's that integration tool set for dx dy, and now this arrow going across means you've integrated dx first. the region of integration is the same. What you're going to compute is the same. Okay, and then down here we see how to implement these computations via command. So this is the integrand. This is solving the parabola for the branches x as a function of y. The int command with a capital I is unevaluated. The int command with a lowercase I is instantaneous. It computes, and that's where the 1/120 comes from. And this is what it looks like if you invoke the multi-int command as a command. Okay, so without any decorations, you get the value. Output equals integral, you get the unevaluated integral, and output equals steps, you get a stepwise evaluation of the multiple integrals. So first you evaluate the inner integral, and you evaluate what you get at the antiderivative at the bounds. This gives you an integrand for a single integration. This is what that antiderivative looks like, and you evaluate it between 0 and 1, and you get 1/120. Okay. The multi-int command in student multivariate calculus has also been updated to know about regions and predefined regions that integration in vector calculus originally knew. So now multi-int knows that. You don't have to go outside the package, multivariate calculus package, anymore to get access to these other options. And so you can define a region, and you get these cases of dy dx and dx dy. So region, but you could also put in things like triangle and circle and ellipse, etc. So Maple now knows those regions in the multivariate calculus package. And as a final word, again, see the pedagogy that's actually taking place. The mathematical solution shows the student what is it they're trying to do. Then in the interactive solution, you'll notice first we show how to get that answer. Then we use Maple to deconstruct that calculation. And we invoke the various tools that Maple has for visualization, etc. Okay? And then down here, if you are looking for an efficient way to implement these computations, and you are of a mind to have students master commands, well, then this shows you how to do it.